Jared Lishtarj, presenting a joint work with Chris Alberti and Shankar Kumar, titled Simple and Effective Gradient-Based Tuning of Sequence-to-Sequence Models. Recent progress in large language models has been driven primarily by increasing parameter size. The largest models are too expensive to train multiple times, so traditional hyperparameter optimization techniques are of limited use in tuning them. This constraint motivates this work, which explores the technique which can update hyperparameters dynamically during training. We use a simple and greedy method to learn hyperparameters alongside the parameters of the model, updating the hyperparameters with the gradient on the tuning loss. We explore the effects of applying this method towards learning a learning rate scalar and momentum for sequence-to-sequence models, specifically for neural machine translation and T5 language model pre-training. The algorithm we apply has 4 steps. In steps 1 and 2, we calculate the gradient of the training loss on the current model parameters, and then update the model, using our current set of hyperparameters. So far, this is just normal vanilla training. In step 3, we calculate the hypergradient on the tuning loss with respect to the hyperparameters of the model update. And in step 4, we apply the hypergradient to update the learned hyperparameters to generate the next step hyperparameters. So for every model step, we also take a step to update the hyperparameters in a direction which decreases the loss on a tuning dataset. This method takes the form of greedy bilevel optimization, where we take exactly one inner step, updating the model parameters, for every outer step, where we update the hyperparameters. Prior work has pointed out the difficulties of learning the learning rate via greedy bilevel optimization, particularly that learning the learning rate with a single step horizon biases the hypergradient update to prefer tiny steps, which effectively halt training. This is referred to as the short horizon bias, and part of what we'll be doing in this work is assessing to what extent this is an issue in practice. This brings us to the experiments. First, training transformer models on neural machine translation. In these experiments, we learn a scalar on the learning rate schedule and initialize the scalar at 1. Running a sweep over meta-optimizer learning rates demonstrates the short horizon bias, as all runs decay towards a tiny learning rate. However, tuning the meta learning rate to interpolate between convergence on the tuning objective and vanilla training still improves performance. For momentum, we again do a sweep over meta-optimizer learning rates and also try different initializations. All runs with sufficient meta-optimizer learning rate converge to a similar schedule regardless of initialization, rising to close to 1 at the start of training and gradually decaying as the model converges. All learned momentum runs, regardless of initialization or meta-optimizer learning rate, outperform the baseline. We now compare these previous results with a Bayesian optimized tuning of the same variables. In both settings, the learned runs outperform the best Bayesian optimized runs and require many fewer runs to reach maximum performance. When we run the same learning rate experiments on T5 language model pre-training, we observe the same short horizon bias for the learning rate, which monotonically decreases to a tiny value. Unlike in NMT, we don't see any gains from tuning the meta-optimizer learning rate. When we look at momentum, we again see a non-degenerate schedule where regardless of initialization, all learned runs converge to the same gradually decaying schedule. However, when we look at performance on the dev set loss, we see that no T5 model has significant performance difference on account of any of the momentum schedules. However, when we learn the momentum and learning rate scalar at the same time, again running a sweep over meta-optimizer learning rate, we observe a new phenomenon. The momentum learns a similar decaying schedule, but the learning rate scalar now grows at the start of training before decaying later on. This is not consistent with the degeneracy predicted by the short horizon bias. And when we look at performance, we see that many of these models outperform the baseline in terms of final performance and steps to converge to the same performance. We get a +1 accuracy point boost on the dev set and a 3.4 times speed up compared to the baseline. This is a promising boost in performance on the training objective, but for T5 we really only care about performance in the downstream tasks. When we fine-tune the guided and baseline models on the downstream tasks, we see that the gains in pre-training are reflected across most of the downstream NLU tasks. In conclusion, we saw that greedy gradient-based HPO can be usefully applied to large sequence-to-sequence models. We showed that although learning the learning rate suffers from short horizon bias, tuning the meta-optimization learning rate can in some situations outperform Bayesian optimized tuning. And we showed that the momentum does not suffer from the short horizon bias, but rather learns a consistent schedule which outperforms optimally tuned constant valued runs. And in the T5 setting, jointly learning the hyperparameters leads to unexplained behavior, which improves performance and speed of convergence. We released the code we use to facilitate further research. If this has been interesting to you, please stop by to chat. Thanks.